Last time on Deep Sky Detail. This experiment was done with broadband filters in a moderately light polluted area. In terms of signal to noise ratio, there's no benefit of longer subframes as long as you're above the read noise. Shorter subframes are fine. What about darker skies? I think there is an extremely credible argument for going as long as you can, like Tim Hutchinson claims. It's too bad I'm in light polluted skies. It would be nice to have some sort of filter that could mimic dark skies, wouldn't it? These results are kind of weird. I wonder what Dr. Detail would think. Think about what? Oh, hi, Dr. Detail. It's nothing. Aren't you in the wrong dimension? It doesn't sound like nothing. Okay, so look at these statistics from my sub-exposure length experiment with narrowband filters. Isn't that strange? What exactly are we looking at? Wait, how can you read my mind? Well, you see, the answer is simple. I can read your mind. What are you looking at? You see, I did an experiment a few months back in broadband using just a luminance filter. I looked at 300-second and 600-second subframes to see which type of frame has better SNR when you stack them. Things were controlled really well. I used real statistics with a real experiment to give a concrete answer about sublength. And I found no difference between the subframes. Now I'm doing a similar experiment in narrowband using my HA filter. Again, giving a concrete answer with real measurements. And I found... I lost connection with your brain. It looks like you'll just have to make a video about it. Oh, okay. Welcome to Deep Sky Detail. This is the third video in a series of videos that examines how long your subframes should be in astrophotography. The first video looked at very short versus normal length subframes. The second examined normal length versus very long subframes, and I found different results for both, and the explanations are given in those videos. Both were examining broadband imaging without any fancy light pollution or narrowband filters. For this video, I've redone the experiment with a hydrogen alpha or HA filter with a 12.5 nanometer bandpass using 150-second, 300-second, and 600-second subframes. So are longer subframes better? We'll get into it. For those new to astrophotography, you may have heard of subframes and are a bit perplexed. Should each subframe be long, or is total integration time really the only thing that matters? That's a question I had for a very long time. If you're new to astrophotography, then let me give you a bit of background. In astrophotography, the things we were imaging are really, really faint. Well, except for the stars. And ideally, we should just be able to take really long exposures to bring out the detail. But it's hard to track an object as the Earth rotates and as the stars move across the sky. So we put our telescopes on mounts that track the stars. Too long of an exposure can be bad because the gears in the mount aren't perfect and you get errors in guiding. The stars also start to get saturated. Plus, there might be light pollution that can wash out a long exposure. So instead of one long exposure, we take several shorter exposures called subframes or subs and average them. This type of averaging is called stacking. With a perfect camera and perfect conditions, the average of the short subframe should be pretty much identical to one longer subframe. Cameras aren't perfect and conditions aren't perfect. So the question is, what is the ideal sub-exposure time for narrowband imaging? Should you go as long as you can, or should you keep the subframe short? To really answer that, and before we get into the experiment, we've got to get into some competing theories. But first, what equipment am I using? I've got an 80mm doublet refractor at a focal length of 600mm. Attached is my ZWO 294mm Pro camera with a 0.8x reducer on an Orion Sirius mount. So it's operating at f6. I'll be using an off-axis guider. The experiment took place in Bortle 6 or 7 skies, meaning there is a good amount of light pollution, but it could be worse. I'll be examining the Horsehead Nebula The Horsehead is a great target for this. There is a lot of hydrogen in the nebula emitting infrared light that my hydrogen alpha filter focuses on. One really important aspect of the filter is its bandpass. In astrophotography, narrowband filters isolate the type of light we're interested in. Hydrogen in space can glow as it absorbs and re-emits radiation from nearby stars or other sources. That light has a very specific wavelength in the red end of the spectrum, which is roughly 656 nanometers. Hydrogen alpha filter tries to get rid of all the other light that isn't 656 nanometers. It may let in 90% of the HA light through, but it's not perfect. It can also let in other light. The bandpass tells us exactly how much other light we should expect. A 12.5 nanometer bandpass hydrogen alpha filter, for example, allows light from about 650 to 662.5 nanometers to pass through it. That means it's including more than just the HA light, which can allow in more background glow from the stars and light pollution. A narrower bandpass, like 5 nanometers, would do a better job of blocking unwanted light, isolating just the HA signal and improving contrast in light-polluted skies. So bandpass is measured in something we call the full-width half maximum, or FWHM. It's a way to describe how wide a filter's transmission curve is at half of its peak height. When you look at a graph of a narrowband filter, the x-axis shows the wavelength in nanometers, and the y-axis shows how much light the filter lets through. So a transmission from 0 to 100%. The filter will have a sharp peak at its target wavelength, for example, 656 nanometers for hydrogen alpha. At the top of that peak, the filter is letting through the most light. To find the full width half maximum, you go down the curve to the point where the transmission is half of that maximum, and then measure how wide the curve is at that height. That width from one side of the curve to the other is the full width half maximum. So a filter has a full width half maximum of 5 nanometers. It means it's letting in light across a 5 nanometer range centered at 656 nanometers. Typically from about 653 nanometers to 658 nanometers. The narrower the full width half maximum, the more precise the filter isolates the desired signal and blocks out other unwanted light, like light pollution or starlight. A wider full width half maximum lets in more light overall, but also allows more background and contamination to creep in. Let's talk about the get more signal on each sub-theory. And this will kind of set off a debate about signal-to-noise ratio in general. Does sub-exposure length matter? My personal view has been too short of an exposure can be bad for SNR, but after you reach a certain point, it doesn't matter because light pollution kills most of the faint signal anyway. But a while ago, I saw a presentation by Tim Hutchinson on the Astro Imaging channel where he said this.
We need to make sure that we're above those minimums, but the real question is, how long can I go? Because remember, the longer we expose, the greater impact we have on our shot noise for every single frame. And then as we stack those frames, the better we're going to be when we're trying to drive that noise down away from the signal that we've captured. In my opinion, I do not follow the advice of some that suggests that, hey, these CMOS cameras are so great that we can take really short exposures and get a great image. You can get an image, but I humbly suggest that you won't get a great image, right? And the better images will come when we make that target signal as bright.
Let's call this the get more signal per sub theory. As you may or may not remember, in my last video on the topic, sub length didn't really matter. Only total integration time did, especially if you're stacking into a 32-bit image. Well, why didn't it matter? And are there times when it does matter? Well, let's talk about the only integration time matters theory. For this part, we're going to... Hold on a second. You said you're doing an experiment. You should explain those details first, I think. Then you can get into the theory and hypotheses. Okay, so let's talk about the experiment. So I've already touched on the equipment that I'd be using in the target, which is the Horsehead Nebula. I systematically altered between 10, 5, and 2.5 minute hydrogen alpha subframes each night of imaging. So it would take 4 2.5 minute subframes, then 2 5-minute subframes, and then 1 10-minute subframe, and repeat. This should help rule out systematic differences between the subframes that aren't due to the actual length of the subframe. And in other words, it helps eliminate third variables like weather on the subframes. Is it perfect? No, but I did end up getting about 6 hours worth of data for each type of subframe, so around 18 hours of data total. This is the printout of the horse head. Do you see this part of the horse head? I took this region right here and divided it up into 60 samples. This was used to analyze the SNR, but I also subtracted the sky glow using this region here to make sure I wasn't overestimating the SNR. I would take a registered calibrated frame, find all the brightness values of the sample, stack another frame with the same sub-exposure time on it, and find the new brightness values for those pixels in the sample until I had stacked all the images. This would give me the signal. I also kept track of the individual pixels within each sample to find the noise. And the noise is just how fast does the signal converge to one value. And it's measured by the cumulative standard deviation of the individual pixels. I also split up the samples based on their brightness, dividing them up into bright, medium, and dim samples. I then calculated the SNR for all of the samples. I did end up throwing out one 10-minute sub, 350-second subframes, and two 300-second subframes. So for the analysis, I used the same total integration time for each type of sub, which was about 6 hours and 20 minutes. To make sure everything is working out correctly, as a gut check, we could take a look at how exposure time changes our SNR measurement for each sample to make sure they seem to follow a typical SNR curve. And it looks like most of them do. We could also, as another gut check, take the final brightness of the samples and see how they correlate with the final signal-to-noise ratio measurement that I calculated. The brighter the sample, the larger the SNR should be. And critically, the relationship should be nonlinear, where SNR should be related to the square root of the brightness as shown by the purple line. A linear best fit shown by the red line should do worse, and it does do worse. The statistics tell me that the nonlinear relationship is better than the linear relationship, and that's good. We're on the right track. Of course, the data are still noisy, but real life is noisy. I took all of the SNR measurements from the 600-second subs and put them into their own group. I did the same thing for 150-second subs and the 300-second subs. I then put them into a statistical model that finds the average signal-to-noise ratio of all of the samples, and critically, whether one type of sub increases or decreases the average SNR. For example, the overall SNR for all the subframes might be around 10, but a 600-second subframe might increase the average by 5 SNR. A 150-second sub might decrease it by 5 SNR, and the 300-second sub does nothing to the average. In this way, I can empirically show how much better or worse a 600-second sub is from a 150-second sub for these data. It should be good measurement. Let me show you the results.
Wait a minute. You still haven't gone over the only integration time matters theory. Why does this still matter, and why is there a debate?
Okay, yeah. So let's talk about the only integration time matters theory for a second. So this is important. There is a bit of math involved to understand the argument, but it's not bad. SNR is calculated on a per pixel basis, and the top part of the SNR measurement is the accumulated signal. The bottom is the accumulated noise. Let's pretend we have a perfect camera, and on one 150-second subframe, let's say a pixel measures 100 photons on average for a deep sky object. That's the numerator. In the denominator, we put that 100 underneath the square root. That's the noise associated with the object. Now let's say that light pollution adds another 1,000 photons to our pixel on average. That doesn't get added to the numerator. It's not part of our deep sky object, but it does get added to the denominator. You just add it underneath the square root. If our camera were perfect, this would be the equation, but it is not perfect. We also have to add in the dark current noise. The longer your shutter stays open, the more dark current noise there will be. It's not much compared to the light pollution, but let's just say it's 2 photons worth of noise per every 150 seconds that the shutter is open. We add that too. All of these numbers I've shown so far really only depend on how long the shutter is open. If we stacked another 150-second subframe,
we'd add another 100 photons to the DSO signal. 100 photons of DSO noise, another 1,000 photons of light pollution noise, and another 2 photons of dark current. But if I took a 300-second subframe, the SNR results would be identical on average to the stack of the 2 subframes. I know that some of you are chomping at the bit, ready to attack me in the comments. You're leaving something out. And yes, I am. There is another type of noise, and this one is not truly related to how much integration time that you have. It is directly related to how many subframes that you have. And that's read noise. Every time you take a picture with your camera, a little bit of noise is added to that subframe. That's what read noise is. Now, let's say that this camera has a read noise of 10 electrons. That means your camera thinks that 100 photons were added to the pixel on average. You square the read noise to get the signal, so 10 times 10 is 100. And you add 100 every time you take a subframe. The 300-second subframe only has one subframe, so it only has 100 added to the square root here. But the stack of 2 150-second subframes has 2 subframes, so we have to add 200 to the square root. It has twice as much read noise.
We've proven it. Longer subs are better in terms of SNR, right? Fine, you're correct. Longer subs are better. But why would people say it really doesn't matter? And the total integration time is the only thing that's important. Well, let's do the SNR calculation. The SNR calculation for the 300-second sub is 4.17. The SNR calculation of the 250-second subs is 4.08, which is about 98% of the SNR of the 300-second sub. That's not much of a difference at all. If we had 6 hours total integration time for both types of subframes, the read noise is such a small proportion of the total noise when there's light pollution that there is less than 1 SNR difference between the 2 stacks. You're not going to be able to detect the difference like that with your eyes. They're practically equivalent. And I found that in my previous video, no difference in SNR for the lumens between the 300 and 600 second subframes with the same integration time.
He's tricking you.
What are you talking about?
Let's do a flashback. The audience will find the keywords and put it in the comments.
The read noise is such a small proportion of the total noise when there's light pollution that there is less than 1 SNR difference between the 2 stacks. You got.
Tell them what the keywords are. See if they're correct.
The keywords were when there's light pollution.
Good.
Hi everyone. Real quick, shameless self-promotion time. I've got something new to share. But first, these types of videos take a long time for me to make. This one took a couple of months at least. From planning the experiment to meticulously examining the data to making sure I've done everything right to the video editing. If you've been enjoying these videos, definitely like, subscribe, and all that good stuff. If you'd like to do more, consider becoming a channel member or a Buy Me a Coffee member. Now there's something new. I've decided to open up some time for consulting work. My background is in cognitive and experimental psychology, and I've done a lot with data analysis, neural networks, and human behavioral modeling, especially for research teams, developers, and organizations trying to make sense of messy or complex data. If you're working on something and could use help with statistics, machine learning, or experimental design, I'd love to hear from you. That said, my time's limited, so I'm only taking on a small number of projects for now. So act quickly and head over to ml-behavior.com, scroll down to the contact form and fill it out. It goes straight to my inbox. No pressure, even if you're just curious, feel free to reach out and start the conversation. Now, back to the nerdy stuff. Okay, in the previous examples, light pollution was pretty strong. It was 10 times that of the deep sky object. Unfortunately, sometimes light pollution can be like 100 times stronger than your deep sky object, or even more depending on the target and how light polluted your skies are. But what if there is very little light pollution? Then the main source of noise that isn't coming from the deep sky object might just very well be the read noise. Let's do those calculations again, but this time we assume only 1 photon of light pollution noise hits the camera on every 150-second subframe. Now, the SNR for a stack of 2 150-second subs is a lot better, about 9.9. But the SNR of a single 300-second sub is even better than that at 11.4. and the difference keeps growing over time. By the time you have 6 hours of total integration time, the 300-second subs have 97 SNR, but the 150-second subs only have 84 SNR. The read noise really starts to affect things, and you might start noticing a difference, especially in the fainter areas of your target.
So basically, the last question we have to ask ourselves before I show you the results is this: does my hydrogen alpha filter actually work? Is it getting rid of light pollution? To help me answer that, I updated my SNR calculator app to show you where the noise is coming from in a subframe. I'll link the video I made of that in the description. I used it to give me a rough estimate of how much of the filter gets rid of the light pollution. Based on the rough estimates of the graph, a 120-second luminance sub has about 4,459 electrons worth of photons of noise. A longer 150-second sub only has 109 electrons worth of noise. So quick back of the envelope math tells me my HA filter is getting rid of 97% of the light pollution. That's pretty good. Did we find a difference between the different types of subframes? Well, let's look at the statistics.
The average SNR of the 150-second subframes was about 8.7. For the 300-second subframes, it was 9.4, and for the 600-second subframes, it was 9.9. So that's a difference of 1.2 SNR between the 150-second subframes and 300-second subframes. Each group of subframes had around 6 hours worth of data. Am I confident in these results? It seems like a small result, but the statistics actually indicate that, yeah, we are very, very confident that the 600-second subframes were the best. The effect was similar for the bright and dim samples, but the overall part of the sky I sampled was pretty dim anyway. So I would expect the very bright areas of the flame to show a smaller difference in SNR.
And this is where I'm kind of confused. We found a very small real-world difference in SNR, but it was very reliable according to the statistics between the different types of subframes. I would have thought that the difference in SNR would have been bigger, seeing as we have gotten rid of so much light pollution with the hydrogen alpha filter, like 97% of it. I thought 600-second subs would get something like 12 SNR, and 150-second subs would get like 8 SNR. But there was only about a 1.2 SNR difference between them.
Well, you're thinking about it wrong, but that's not surprising.
Oh, hi, Dr. Detail. I didn't see you pop in.
You compared your L filter to your HA filter to see how much light pollution you're filtering out. But you did not compare the light pollution noise of just your HA filter to the read noise. Just look at the HA filter by itself.
Why would I do that?
Just do it. You'll figure it out.
Okay, so let's try this. We'll put in all of the values into the SNR calculator to get a rough estimate of where the noise is coming from. The sky noise, or the light pollution noise based on the SNR calculator app for a 150-second subframe, is around 110 photons, measured as photoelectrons. And the read noise is only 4. Modern CMOS cameras and some newer CCD cameras have very low read noise. I get it now. Even though I've used a hydrogen alpha filter to get rid of 97% of the light pollution, there's still enough light pollution getting through that longer subframes aren't having as big of an effect compared to if there was no light pollution. Light pollution really sucks. Link to the t-shirt is in the description. Even through a filter, enough of it's getting through that it hurts my SNR. That's crazy, but at least my read noise is low. I had enough data overall from the different types of subframes to find an actual difference between the subframes, but it turns out that the difference isn't really that big. I wonder if narrower bandpass filters would be better. So what is the takeaway then? Well, mathematically, longer subframes are always technically better than shorter subframes, all things being equal. And that's because read noise gets added based on how many subframes you have. But even a little bit of light pollution getting through can really decrease the effect of sub-exposure length on the overall final stacked SNR measurement. And modern cameras control read noise so well. If you're even in moderately light polluted skies, using a 12.5 nanometer bandpass hydrogen alpha filter, you won't get very much benefit exposing for longer each subframe. So I think for my next test, I'll examine what happens with longer F ratios. So what would happen if I went to an f10 and instead of an f6, and how much better narrower bandpasses are. Thanks for watching.